Hi, welcome back. Today we're going to talk about Chapter 2, and the topic for Chapter 2 is kinematics in one direction. And if we're going to talk about what those new words mean, let's lay down a little bit of foundation of some terms as we start to explore physics. The first one is pretty much this first semester, it's all going to be mechanics. And mechanics is the study of motion of objects. And when we study motion, there's two main ways that we're going to look at things. And one is what we're doing now, which is called kinematics. And kinematics is the description of how things move. So you're going to be able to quantify things, make graphs of them, have types of measurement and units and all this stuff for how objects move. Later, we're going to be doing dynamics, which is why objects move. And those are two very separate things. Okay? Now, first of all, we're going to be doing right now translational motion. And translational motion is when you have motion without rotating. All right, so we're not going to be spinning objects yet. That's going to be Chapter 5 and later that we'll be doing that. And so what are some examples of this? Can you think of an object that is moving without rotating? What would be something that we could describe the motion of? All right, can you think of any examples in your head? Any kind of motion of any object? You might think of some sports or all kinds of things, or what you've been doing today. So how about a moving car? We do a lot of car problems in physics because it's such a common thing, and all different ways that we move in a car. And how about a falling rock? Okay, it's a little bit different behavior there. How about, if you like sports, how about a baseball throw? Okay? So those are just some examples. You may have had some other ones that would definitely apply here. Okay, so the focus of this chapter, we like to start off simple, and physics often oversimplifies things, just so that we can be able to understand and actually come up with quantities without needing a computer to do it. But the focus of this chapter is on straight line motion, okay? So we're not going to be doing the baseball throw this chapter, all right? We can do this, and we can do this in certain circumstances. So we're going to have a car moving down a straight road, all right? We're going to have a rock falling straight down, okay, in a straight line. The baseball throw, not going to work out so much for this. Okay, we're also going to work with what we call the particle model. The particle model, once again, we love to simplify things, is a simplified version of how an object is moving. We replace an object with a point, like literally we can draw a small dot to represent an object and then show it moving. All right, so like this, it was here, it was here, it was here, and the object we just draw as a small dot, even though the object might be a car or something else. It definitely simplifies things. If we do that, an example, move this up a bit. See what? Oh, I couldn't see my little one, sorry. Example of this would be, for instance, if you were to throw a hammer. All right, let's see if I can do these hammer drawing skills. Okay, so we have a hammer. And imagine if you were to throw it, or axe throwing is really popular these days. I should have drawn the axe because it could definitely be way easier. If I were to draw it, whoops, yeah, I'm getting into trouble trying to draw it upside down. Okay, then definitely we can see it's going all over the place. All right, okay, I'm doing a really bad job right now. Okay, I'm going to turn it into an X. All right, so if we throw that, it looks like it's going all over the place. If we follow it, if you follow this, all right, then it's definitely a different thing than if you were to follow this part and it's all over. However, if you pick one point, we're going to hope, if I did a good job, one point on the object should follow some kind of a path that might have some kind of a formula for it. I definitely didn't do a good job here because it's going off of that path, but just so you realize, we pick one point on an object and we can just oversimplify that whole object looks like that. All right. So the other thing we need to take into account is something that's called frame of reference, okay? Whenever we make measurements, which we're going to come up with some quantities in just a bit, every measurement must be made with respect to a reference frame. We need something to call kind of our origin, if you'd like to say. How about, here's an example, what if you're walking at 5 kilometers per hour? All right. That's not clear enough. I could make this a little more complicated if all of a sudden I said you're also on a train that's moving at 80 kilometers per hour. All right. So if that goes on, then how fast are you moving? Well, it depends on with respect to what? With respect to the train, you might just be moving 5 kilometers per hour with respect to, in reference to the train. But in reference to the ground, okay, with respect to the ground, you are not, right? So we can say with respect to the ground, how fast would you be going? Well, that kind of depends. Which way were we moving with respect to the train? If the train was moving this way at 80 and we walk this way at 5, then our answer would be 85 kilometers per hour with respect to the ground. If we were moving in the opposite direction to the train was going, right, then with respect to the ground we'd be only going 75. And again, our speed also could be 5 if you just, if you said with respect to the train, okay? So we definitely always need some kind of frame of reference. Normally, if it's not stated otherwise, it's considered to be the ground, the earth, okay? The other thing we need to put into place is that we use a coordinate axis, like we're in math class, I hope. We have north, south, east, and west that we use for reference many times, and that can be on the ground, or we can use up and down. And what the general thing we normally consider, just like if you were in math class, that east and north are considered positive, and west and south are going to be considered negative. All right. Sometimes if we're just doing a simple problem where there isn't a change in direction, all this, then, you know, if you drop a ball and I say, how fast is it going, then we can just make that a positive number, definitely. And how fast isn't very specific either. But if we're talking about velocity, then, officially, we like to consider down negative. Okay? All right, so all those things need to come into play when we start dealing with motion. Okay, make sure we fit this. All right, so let's talk about our first term that we need to know, and that is displacement. Now, if we're going to talk about displacement, let me first define what distance is. So this one's the easy one. Distance, very layman's term, is the total length covered. So that's what your car odometer measures. So the odometer, like the trip meter and all that stuff, how far did you drive? If it's keeping track of how far you're driving in a car, the total distance you did, okay? So if you look down at some kind of measurement, or if you have a watch and it's keeping track of the mileage you've done, that is the total length covered. So you're just all over the place, and it's going to map that all. It's going to measure all of that. That quantity, by the way, is scalar. And scalar means it doesn't show direction. You don't know where you went, like on your car, the odometer. It doesn't know which way you went or anything. It's just the wheels were spinning, and it was measuring how many times the wheels rotated and how much length you covered, okay? Displacement is a very physicsy term, okay? Is the change in position of an object. Actually, it's a math thing too, because you deal with this if you do graphs and you were to find in your change in x, okay, then that would be an example. And in fact, this chapter, we're trying to keep things in one dimension, so we're just going to call this x. We don't care about y. We can change x and y at the same time. We know this, but we're going to just make everything real, linear this chapter for ease. All right, so we're just going to use x for our term. All right, so it's the change in. Now, change in, we represent many times with a triangle, and that triangle is delta. And so delta x means change in position, and that is our displacement. Now, how do you find change in position? Just like in math class, you would do with a graph. You would take x2 minus x1, or you could write x final minus x initial to find this. All right, and if this equals 0, then you have no displacement. All right, so it's relative to its starting point. This is really, really important. Okay, where did you start? Where did you end? You're going to subtract the final minus the initial position, not the other way, because you can sometimes get a different answer. Okay? All right, we say that this is a vector quantity. This is a new term for us. And a vector is a quantity, unlike a scalar, it has more information. It has both magnitude, and magnitude is a fancy word for size. That is the number. So it's not only a number, but besides that, it has a direction. Okay? It's a number and a direction. So imagine you're a Boy Scout or any kind of navigator, and you had to go somewhere. You don't just want to know you're going to go 2 miles. You need to know I'm going to go 2 miles in a northwest direction. All right? That would be considered a vector quantity. If you just said 2 miles, that isn't as informative, and it is not a vector. Okay? So it has both a number, which would tell you how big the amount is of whatever measurement you're making, and a direction. Okay. You walk from 0 to 30 meters and then to 20 meters. Let's do a number line question. It does seem like math class now, doesn't it? Okay, so we have a number line here. I want to know both distance and displacement. Okay, so I draw a number line if you need to. Here we go. So we're going to start at 0. We're going to go to 30. Okay, and then we're going to go to 20. All right. And when we do that, what do we got here? What is my distance covered? Well, I had to go 30 meters, and then to get to 20, didn't I have to go another 10 meters? So I have 30 meters and another 10 meters, so I moved 40 meters. Remember, total length covered, okay? The total distance I went was 40 meters. However, what is my displacement in this case? Displacement, delta x equals x final minus x initial. My final position was what? Right there, 20. My initial position was 0. So, there's my displacement. My displacement is 20 meters. And you go, well, Ms. Jones, you said that it can't be just a number, okay? It has to have a direction. Okay, so based on my number line, I could say to the right. I also don't completely need a sign right now. If this was the only kind of movement and I knew that, this shows direction. The positive sign shows direction, right? Remember I said positive is either up or to the right. So I could do that, or, right, you could have said east. Okay? In the end, we went from here to here. This delta is my delta x, right there. Okay? All right. Let's do some more problems. The more you see, the more, you know, you kind of understand the concept, and the more kinds of questions I can ask you, and you're going to get them right. Okay. So what if this time I went from 20, this is my starting point, my initial, and I went to 0? Okay? What's my distance? Well, I went 20, right? I moved 20 meters. This is, you know, if you had a smartwatch, it might be logging that, and you'd know that. Okay? What is my delta x in this case? Well, I have final, right, minus initial. See, here is where I get a negative. That, again, is showing me my direction. Okay? Yes, this can be negative. Displacement can be negative. It is telling you you ended up to the left of where you started, or to the west of where you started, or below where you started, depending on the problem. All right? So, displacement can be negative. Can distance be negative? No, because it's this the total length covered. All right? So this is always positive. Okay, great. All right, so that's pretty much all. So there's distance is scalar, displacement is a vector, and those two quantities are our basic way to describe motion. Okay. The next thing we're going to use to describe motion is velocity. Now, we're going to start with average velocity because it's the easiest one to do, and then we'll get into instantaneous velocity. Okay? But to understand velocity, it does help to first talk about average speed. Okay, average speed. What most people know speed. What do we know about speed? All right, like in a car. You're speeding in a car, all right? Or you can run at a certain speed. What does that really mean? So, what are we going to do? So, speed is distance divided by time. And that's average speed. And in fact, in physics, many times we draw a line over something to represent that you are getting an average number, all right? Average. So if we know we traveled a certain length and you know what time you did it in, you can get the average speed, all right? You don't know what you're doing all the time, every moment in time, but you do have an average, okay? And keep that in mind. For instance, if you go 60 miles in 1 hour, and therefore 60 miles per hour, that doesn't mean you're doing that the whole time. That would be the average. Okay. All right. How about average velocity? Ooh, this is a physics term now. And again, here we have a symbol V for it, and we draw a little line over it to represent its average. And what are we going to do? Well, since it is a physics term and it's going to be a vector, instead of, we can't use the word distance since that's scalar, we're going to use the word displacement. And so average velocity is displacement over a time or time interval. All right? And we can write that with our symbols because we know displacement was delta x, and then our time interval will be delta t. Now, with time, many times we just put a t. It is assumed to be a time. We are not normally given a t final and a t initial and you have to subtract. That would be the case if you had a clock and it was already running and you know the start time of the clock and the end time of the clock, and you would have to subtract those two. That's very rare that a problem would do that, although sometimes in a lab we do have that situation. We have a gravity lab where you actually have to do that. But for most cases, you're going to be starting a watch at the beginning of the time interval and then ending it. And so it started at 0, and so you just have a t. Okay, So we can make that a little easier. All right. The best way to see what we are doing is to get a sample question here. So let's do this one. Let me move this up a little bit so we can see our number line and the question. All right, if we are going from the origin, okay, and then we go to 30, and then we go to 20. Oh, we did that before. And we're going to do this in 50 seconds. Now, I put these decimals here to indicate that I have two significant figures. It's not really the proper way, but I didn't want 3 because that was a bit ridiculous. When I printed this number line, it only shows whole numbers. I realized that, and I just wanted to show a little bit more detail. I wanted two figs in a number. Let's just say that. Okay, so what are we going to have here? Let's do some math. So if I want to find out my average velocity, what am I going to do? Well, what was my I need displacement over time, and my displacement is 20 meters, right? And I did this in 50 seconds, right? And so I get 0.40 meters per second. All right? So that would be my average, and if you want, so you don't lose that decimal, okay? All right, so what about my speed? Is my speed going to be the same? No, because remember, my length traveled was 40 meters. All right. And so this answer is going to be twice as big. All right. So in this case, my average speed is twice as much as my average velocity. Okay. So, okay. When would these be the same? Can they be the same? Can your velocity and your speed be the same? Yep. What has to happen for that to be the same? What circumstances would make your velocity and speed the same? What did I do here in this picture that made them not the same and made my distance traveled not the same as my distance from my starting point? Pretty much that's what I'm saying. And that was this thing right here. I turned around. If I didn't turn around, we would have been set. All right. If I just went straight to one location, if I just went to the 40-meter mark, and then both the velocity and the speed would have been 0.80. Okay? Because then my distance and my displacement would be the same. So the answer is, to make your velocity and your speed the same, you have to have the same displacement. To have the same displacement means you have to travel in a straight line. That's number one. It isn't completely full because, what about this question right here? Can you have a negative velocity? Yes. You know why? Because we've seen our displacement can be negative. Okay? Can you have a negative speed? No. And we've seen that because our distance can't be negative. Distance is just total length traveled. Okay, so how about let's make our answer a little more complete on when velocity and speed are the same. Can I just say things must travel in a straight line? Well, I could, what if they both went this way? If they both went, oh, my marker's getting tired already. If they both went this way, then my velocity would be negative while my speed would be positive. So if I'm going to say when is velocity and speed going to be the same, I have to say you have to travel in a straight line in a positive direction. So either up or to the east or to the right. Okay? All right, so those are little nuances. Once we learn some terms, we find out some little nuances that make things a bit interesting. Now, the other thing I want to say, oh, and I had another formula I just kind of threw off to the side, that there's another way to find average velocity. That is, if you know your initial velocity and your final velocity, let's say you were going 20 meters per second, and later you were going 40 meters per second, right? And so you were changing your speed, and you were doing it uniformly, then we know how to find an average, right? 20 plus 40 divided by 2 would get us an average between. So your average then would be 30 meters per second. Okay, so that's a second way, depending on what information. If you didn't have how far you went, then that would be a way. The other thing is, notice when I get an average, it doesn't represent where the velocity in which you started or where which you ended if you are not uniformly going that velocity. If you don't change your speed or your velocity, then, or your rate, then it's going to be the same. But be very, very careful with average speed and average velocity and assuming that's what you're doing at time 0 and time f, because it's not true unless you're going constant, all right? So in this case, this is my average, but you were going this to start with slower and you're going faster to end with, right? Keep that in mind, all right? And if you're doing it uniformly, when does this occur? Would be at, t 1/2, at 1/2 the total time, okay? So keep that in mind. All right. That kind of leads into this discussion here about instantaneous velocity. Let's look at some graphs, and it's best to see graphs, okay? Instantaneous velocity is the speed and direction, because it's a vector, at a particular instant. Okay, let's look at some graphs that are really, really important. And you'll get thrown graphs like this all over the place, especially in this chapter. So this is a graph of x, okay, versus t. So you can kind of think of it as this, either as distance or displacement at this point. This is your position and time. And what do we see here? What do we see happening in this case? Let me grab my notes here so I can be reminded of what I'm doing. For our first time interval, let's do some velocity here. In 5 seconds, what did we do? Let's do off to the side. Can you see right here? V is, let's do displacement, 15 meters, 5 seconds. So what's my V going to be? 3 meters per second. Okay? What about my next time interval? What about from 5 to 10 seconds? What do I know? All right. Or I can do the whole thing. I can do the whole time interval. In 10 seconds, right, I did 30 meters in 10 seconds. What does that equal? So this means later I was still going 3 meters per second. What did we find out about this graph in both these cases? Didn't we just do that and didn't we just find out that? And then we did that, and I could have done this. And they're all going to be the same. What's going to be the same? The slope. Didn't we just find rise over run? Didn't we find the slope of this line? And if we see x versus t, so the slope of x versus t is going to be your velocity, okay? All right, or if this is distance over time, then it would be your speed. We definitely see there is a constant slope here, and if you have a constant slope in this graph, you have a constant velocity, all right? This is in this time interval. We have measured what your velocity is, and it is the same in this time interval. How does this relate to instantaneous velocity? Your instantaneous velocity is really what's happening. If we could make this interval of time super, super short, all right, think like limits, then we could find out what that is. All right, at a very super small interval of time, our average starts to become our instantaneous. All right, let's look at this graph, because this graph is a little bit different, right? We don't see, what are we doing here? There is a graph that looks like this. First of all, it's a curve. So we have displacement versus time, that's a curve. And what are they trying to do right here? They're trying to find, they took the tangent of that curve, and right there, if you have, again, a rise and a run, you could find out the slope of that line. And the slope here is not the same as the slope here. Isn't this slope greater than this slope? So if we want to analyze this, we see that we have a changing velocity, and in fact we have an increase in velocity. You can also see that if you look at, if I can scoot this over a little bit. Maybe not, come on, there we go. All right, if we looked at that table of information, then we see that this is growing more exponentially. Okay, all right, so we see there's and all of these points here would be, where you'd find the slope of those would be different velocities. So we definitely see that our instantaneous velocity at a particular time is not the average velocity. Here we can see this even better, where this graph, instead of distance versus time, is velocity versus time. Let's see if we can study this a bit. All right, so what's happening right here? No velocity. Imagine you are driving a car, or you get in a car. This is when you're parked, all right? And then you hit the gas pedal, and you start going faster and faster. So your velocity is increasing. Here, these are individual velocity. This is V1, V2, V3, V4, all right? And we see we have a change in velocity, all right? But how am I changing my velocity? I'm uniformly changing my velocity there, all right? And we call that word, that's our next word that's coming up, an acceleration, all right? Our velocity is changing. Every single point here are these are my instantaneous velocities, okay? Or anywhere on this whole graph. Individual points. All right. Here we see on this graph, it looks like nothing is happening. You have no slope. We have no slope. Does that mean you're not moving? No. If you have no slope in this graph, it means you're not changing. So we are not changing our velocity. We are going steady, or a uniform. We like to say uniform velocity right there. All right. Do you realize a graph of this looks like this? Okay. You have one velocity. If you take the slope, it would be the same slope every time for this graph, but here there's no slope. Okay. All right. Look what's happening here. Your velocity every second is going down. All right. So you are slowing down here. And we call that a deceleration. Again, terms that will be coming up in a second. All right? And you're uniformly doing that. Every second you're changing by the same amount. Okay? And then what do we see here? This is kind of wild. Oh, this is a curve. We have a velocity versus time graph curve. If that's the case, not only are you changing your velocity, you're changing your velocity at a changing rate. This is pretty complicated. We will not do math problems like this, but I can show you pictures on a graph, and you can make some statements or pick an answer for a multiple choice question about something like that. But we will not be doing math with an increasing acceleration. Okay, now I've just mentioned that word acceleration a few times. We better define it then. All right, so acceleration, and we're going to start again with average, just like we did with when we did velocity. Our average is the change in velocity over change in time. So delta v over delta t. Again, if we're going to do that, so our change in velocity is v final minus v initial over t. So this is set up just like how we set up our formula for velocity with delta x. All right? It's the rate at which velocity changes. All right? If you have no change in velocity, you have no acceleration. If you are speeding up, okay, if you are going fast, if your velocity is increasing, then we have a positive acceleration. Okay, here is the question I always ask. What three controls in a car make it accelerate? Let's see if you can think of the answer for that. Now, most people have no trouble coming up with the first one, all right? Because in this country, we sometimes have a word for this as one of our controls in a car, all right? All right. Sometimes, how about this? We can use the word gas pedal, aka the accelerator, right? So if you push the gas pedal, you can make the car change its velocity. It was at first have 0 velocity, and then it's going to be more. Yay. What's another way to be able to change your velocity in a car? All right? What do you think? Well, it's the other pedal. All right? It's the brake pedal. And don't spell brake like it's going to break in half. The brake, all right? The brake can definitely change your velocity, right? Okay. Now, if you're really savvy in your mind, you've thought about a third control in a car, all right? Now, some people want to say, oh, the shifter. Well, most people in America, first of all, have an automatic. But even if you have that shifter, we're not going to get to count that, because that is just not really going to make you go faster. To go faster or slower, definitely you need these two. You say, well, what is it going to be? Okay, and again, you can't say emergency brake. That's kind of cheating too, because that's going to be our brake. All right, so if you've really been thinking about what velocity is, and keep in mind that as a vector, then hopefully you came up with this one. Put a little exclamation point, because you should be excited if you came up with this one. So the steering wheel, and you go steering wheel doesn't make me go faster and slower. I can turn the steering wheel, and if my car speedometer said 40 miles per hour, I can turn, still it'll say 40 miles per hour. So I didn't change at all. Well, remember, your speedometer is literally that. It's a speedometer. It is measuring your speed. But velocity is a vector. And even though you're still going 40 miles per hour, if you change direction, then you have changed your velocity. Okay? Because if you were first going 40 miles per hour north, and now you're going 40 miles per hour northwest, then you do not have the same velocity. Okay? So the key here is your steering wheel can make you change direction, and changing direction changes your vector. Okay. How do I prove that? Because people are always like, that's a cheat. That doesn't count at all. Well, it does. Because your body can be an accelerometer. You can measure and know if you were accelerating. And that's because later we're going to find out to accelerate means you have to feel, you're going to experience a force. And you can feel a force. So how do we do this? So what about if someone all of a sudden pushes really hard on a gas pedal? What do you feel? Well, don't you feel the car kind of like lurch forward? Right? If you weren't holding on or paying attention, right? Whoops, I'm sorry. Not if you're, I said hit the gas pedal. Sorry. You go back. Your head's gonna hit the headrest when you do this. and, right, you're going to feel that the car took off without you. Okay. How about if it's, so now I got the other one. Right, if someone hit the brake and isn't very good, right, then you lurch forward, right? You feel like, you know, you needed that seatbelt to kick in to keep you from flying forward and hitting the dashboard, right? If you had some severe braking going on. And what about if you turn? Don't you feel yourself, right, when you turn, that you're thrown sideways, right? So we definitely can feel acceleration. How about if you're in an airplane? Do you feel that you are traveling at 400 miles per hour when you're in an airplane? Nope. And why don't you? Because you're not accelerating. All right? You don't feel velocity, but you can feel acceleration. And it's a test for you to know if you do have an acceleration. So when do you feel that you're moving in a plane? Right? When you take off, when you land, and when you do a banked turn, right? If you're turning into an airport or whatever, okay? Then you definitely feel it. All right. How about this instantaneous thing again? All right. Instantaneous acceleration. When the change in time approaches 0, you can make average acceleration become instantaneous acceleration. Here's this, I was kind of hinting at that before. If you make a time interval really, really, really small, then we don't have a big graph triangle anymore that happens over a large period of time, and you don't know when that point is, or again, you have this curve, and you're not really, you know, you have all these, and you really want to know one data point, but all you thought you could get was this. If you make that triangle really, really tiny, then it gets close to being instantaneous. And so you could set this up as a limit as time approaches 0 of delta V over delta T. Then we can say, then we have instantaneous acceleration. All right? So we can talk about having a changing acceleration, like I said, but we're only going to do problems that have uniform acceleration. All right? So it's not changing at an odd rate. So we're only going to do problems V versus T, all right, that our velocity is uniformly changing. Okay, let's do a problem here. What is the acceleration of a car that goes from 0 to 30 meters per second in 10 seconds? Okay, so, well, we can do this. So we say that A is V final minus V initial over time. Our final was 30, our initial was 0, and our time was 10 seconds. Whoops, I didn't put my units up here. Meters per second. All right, and what are we going to get? Well, 30 divided by 10 is 3, so, I gave myself 3. So we have 3 meters per second. Okay? Well, what is this telling us? Well, this is telling us that in the first second, what happened? In the first second, right, we went from 0 to 3 meters per second, right? At the end of 1 second, we were going 3 meters per second. At the end of 2 seconds, right, if we're changing by 3 meters per second every second, then we're going 6 meters per second. And at the end of the 3rd second, right, we're going 9 meters per second. So this is we have an acceleration because we're changing our velocity, and this is a case, so this is showing a uniform acceleration. We're assuming we're uniformly doing this. If you had turbo in your car, this would not be uniform, but we are assuming we're just evenly pushing on your accelerator or your gas pedal. Okay? So if you carried this out for 10 seconds, then you would hit your 30 meters per second. All right. If the car kept accelerating for another 5 seconds, what would its final velocity be? Well, if you just want to do this logically, you were going 30 meters per second, and And then you did this for another 5 seconds, and you could say, oh, I'm going to add another 5 seconds worth of change in speed. And what would I get to, right? So, so 5 times 3 is 15 plus the 30 is 45 meters per second. So there would be our answer. If we want to do this with a formula, I can really just switch around my formula for acceleration. My acceleration, right, v final minus v initial over t. Well, what if I solve this for v final? I would see that v final equals my v initial, that was that 30, plus an additional amount, that's my acceleration times my time, which is really this. My acceleration was 3 meters per second times another 5 seconds. So this is really nice to see view like this. If I want to know my final velocity, it's whatever I started at plus an additional amount. And this a times t is a velocity. And we can see that by our units. Meters per second times seconds, one of those seconds goes away. Here we have our units for velocity. This is velocity, so we can add our meters per second with meters per second to get my final velocity. Okay? All right, so those are 2 ways to view that problem. All right, how about this next one? A car goes due east at 15 meters per second and brakes. It takes 5 seconds to slow down to 5 meters per second. Okay? How do I set this one up? All right? Some people do this quick and then they can get it wrong. Acceleration is v final minus v initial over t. What is my final? My final was 5 meters per second, and my initial, right, was 15 meters per second. And I did this in 5 seconds. All right, so what do we got? Here's the key. The top is -10, and the bottom is 5 meters per second, and then we get, what do we get? We get -2 meters per second. Let's talk about those units real quick. We can write meters per second, or in physics, we like to write meters per second squared. Okay? But this doesn't mean as much many times. If you're confused on a problem, especially early on when you're new to this, meters per second, okay, or your meters per second every second seems to make more sense to people. All right, why is this negative? This negative is because you are slowing. All right, or how about this? It's going to mess some people up. How about if I say your acceleration is in the opposite direction of your velocity? Okay? Your acceleration, remember it's a vector and it has direction. Okay? How about if I say you're accelerating which way? If your car is going to the east, that means you're accelerating west. Does that mean you're going backwards? If you have a negative acceleration and it's directed to the west, does that mean you're going backwards? Nope, doesn't have to. All right, this car was going to the east, but it was slowing down. Its velocity was this way, but its A was this way. All right, ooh, more interesting questions. All right, that could be asked. How about this? A dragster has an acceleration of 10 meters per second, or 10 meters per second squared. How far has the car traveled in the first second? Oh, nice numbers, Miss Jones. Thank you. Making this super easy. You give me the acceleration is 10 meters per second squared. How far did it go in 1 second? I want everyone to quickly jot something down. Do you have an answer for this? Set up the problem. Right? Set up the problem. Or do it in your head if you think you want to. What should we do for that? You have an answer? Okay. Let's see if it matches my answer. Okay? ask for how far. How far and how fast are not the same thing. All right? I wanted to know that. Okay? I wanted to know that. Okay. And then my number one thing for new physics students is when we're dealing with these few chapters that are coming up about speed, velocity, and acceleration, all this stuff, is you cannot use top speed to figure out how far you're going. You cannot use top. Our only formula we have that includes delta x is this. Average. Average velocity is delta x. So if I'm going to ask about this, you cannot use instantaneous or your top speed. You cannot use your top speed. Okay? All right. So what we do know is after 1 second, 10 meters per second squared times 1 second, right? We lose one of those. We are going 10 meters per second after 1 second. We started at what? It's a drag racer. He started at 0 meters per second. And after 1 second in time, he's going 10 meters per second. How many of you thought the drag racer was going to go 10 meters in 1 second? It's not.
Miles, please call extension 7012.
All right. So, what's the real answer here? What's the correct answer? Well, the only way I can solve for this is I have to have an average velocity. I know, that's why I gave you that second formula. If you start at 0, 0 plus 10 divided by 2 gives you your average. My average velocity is 5 meters per second. So if I want to solve for delta x, which is average velocity times time, I have to take my 5 meters per second and times it by a second. And then I will find out my dragster has only traveled 5 meters in the first second. Here's another question. So hopefully you realize if you quickly thought it was going to go 10 meters, very common mistake. Don't let yourself fall into that mistake again. Everyone is allowed to make mistakes and should be making mistakes. Otherwise you're not challenging yourself. If you thought 10, you need to make big note of this so you don't do it again. Okay? If you don't change how your mind thinks, then you're going to make the same mistake every time. You're going to do it the same way. Okay? So definitely keep that in mind. In the second, is it going to go the same distance? Absolutely not. Because in the second, what do we know? He's going to be going 20 meters per second. His average is not going to be the same. You could find out how far he goes in the second, or you could find out what the average is in 2 seconds, however you want to take a look at this. And next lecture, we are going to see a formula that helps take this into account so that you don't have to, didn't we have to do really 3 things here? We had to find out our final velocity, we had to find an average velocity, and then we had to find out how far. We're going to have a formula coming up where that'll be all in one. We can solve that, so we don't have to make that mistake. But with the formulas we have, totally can solve this. It just takes a little bit of time.